we're still slightly behind, slightly. We got a little bit to forces and torques last time. We're mostly going to talk about forces and torques today. What I've decided to do is MRI materials and NMR is really interesting, but we should talk about it once we've talked about this. So I'm just going to move MRI and materials down to here. We've actually talked about what a quantum state is. That would make a lot more sense than just sort of BSing it for now. So today we'll do a little more forces, some stuff on torques, and then get a little bit into Faraday's law. But we have all next Tuesday also to talk about Faraday's law. And then we'll be somewhat caught up, and we have to stay caught up so that we have this whole week to review. I enjoyed our last review so much, I'm willing to review for a whole week. Serious, I'm not joking. It's easy lectures to write. Much more fun for me. And that's probably what you would rather do. So I'm trying to keep us on schedule so that we have our review week. Okay, let's see, where were we? Let's see. So we talked about the motion of a charge in a magnetic field. So if you have a uniform magnetic field like this, so this is my uniform field out of the board. And it's the little vector arrowheads coming at you here. And like this, like that. So there's the B field. Uniform B coming out of the board. All right. Can you dye your hair purple, or at least temporarily dye? No. I would not want to be associated with that round comment. What concepts in the schedule will the test cover? We don't know yet. Not sure. The finals, last time, is it comprehensive? Is it not comprehensive? Well, you got to have the first part to be able to do the last part, so it's sort of pseudo-comprehensive. Well, we can't really do that in this exam, because the three parts are completely independent. I mean, we have light and waves, and then we have the electric field, and now we have magnetic field and modern physics. So it's not, the class isn't comprehensive, so we're not sure how we'll do it. We can't have a whole final exam just on the magnetic field and modern physics. That would be weird. So we're still figuring it out. Actually, I think we made a decision. I just can't remember what it is. Okay, so uniform B field. We talked about if you have a charge in this uniform B field, say, let's imagine an electron, negatively charged particle. How will it move? Ask yourself, see if you're following along. How will it move? The answer is it won't move, because I haven't made it move yet. Because for the magnetic field, charges have to be moving to create a field, and they have to be moving to experience a force from the magnetic field. So here it's implied that it's at rest, but now if I say, okay, let's make it move, I'll guess which way it would make sense. Now, a negative charge moving up. Let's think, which way did it move? What kind of motion was it? Let's see, F was QV cross B. Remember, F, the force it feels is QV cross B. This is just a reminder, this isn't the official notes here. So F, let's see, B is this way, fingers this way, but I want to curl them towards B. Because B is sticking out. The force must be that way, right? Except, wait a minute, that's just B cross B. The Q is negative because it's an electron, so the force is that way. You have a negative E, negative 1E in front of B cross B. So unfortunately it's this way, I guessed and guessed wrong. So it would move, I'm sorry, I guessed and guessed, that's still wrong. It has a velocity this way and an acceleration that way. And we talked about before how that makes a circle. Because as it starts to curve, the acceleration will always be perpendicular to the motion. So you end up with circular motion like this. So charged particles move in uniform circles in a magnetic field. That's really not why I drew this. I drew this so we can talk about, so we can keep talking about the mass spec. Let me put this back. The uniform field is back. Get rid of that reminder. And talk about mass spec. Because it's a good example of this that you might actually use someday. That lets you measure the mass of molecules and identify what molecules are present in a sample. All right. So let's see. My next thing says finish the cocaine video. Okay, so I guess that's what we have to do. So remember the way the mass spec was working, we were right to the point where the ions were about to enter the magnetic field, and then the YouTube video died. It stopped scrolling. So let's finish. Let Wesley, or whatever his name was, tell us a little bit more about what happens inside that machine. Here we go. And I'm going to set him, he's a little slow. I'm going to set him not quite my speed. How about 1.5? charges on the ends? Okay, let's just forgive that. He's an analytical chemist. It's okay. Okay? It's a magnet creating magnetic field is what they're trying to say. Okay, here we go.
As the molecules all charged, the magnet force what they cause. The small,
bending, right? They're making circles in the magnetic field just like this.
The stimulant of choice for alcohol classes became also known as Zucker, Bernie, the Big C, Blow, Charlie, Peggy Janelle, Laura Snow, King, Mamma Coca, Living Marshall Power, Monster, Nose Candy, Stardust, White Lady, Yayu, and Indie Massage is an alcohol expert.
Will be on the exam. So here's your structure. He's adding up the atoms to see how much it should weigh.
Nitrogen 14.007, oxygen 15.999, and hydrogen 1.0079. All added up to a total of around 304. That's the number we have to look out for.
Results are ready. You see here we have a massive peak at 304, a massive number, because this number is a positive data. So when you talk about
let's see the graphic. There it is, 304. A big peak at 304 indicates that there's a molecule in that sample that weighs 304 atomic weight, which is the same as cocaine. So a mass spectroscopist would say there's cocaine in the money. Well, there's a lot of molecules in the world. Right? My guess is there's an environmental molecule out there, like something in your sweat, that is also 304 and has propagated this urban legend that all money has cocaine in it. I could believe it in the 80s, but not today. Can't really be sure it is. So I don't know. I think you would have to, I don't know how you would figure it out. But I think if one of you did a big study of environmental molecules that also show up at 304 and could disprove this myth, it would be the key to internet fame. So I recommend you work on that. Okay? But now we're going to talk about what was left out of his description of the mass spec. That's actually a very good way to review and think about fields. It would be a perfect final exam question because it does cover two areas. And the deal is, remember when we talked about this circle, what was the radius of the circle? We set QVB equal to MV squared over R. We said that the force causing it to go in a circle must be the magnetic force. So that's why the top of a mass spec will look something like this. You'd have some source of the ions here. Something happens down here to your sample. Ions come out, and we'll say they're positive ions now, because it's a molecule with an electron drift off of it, and it goes like that. So the way that you separate molecules of different mass is they go to different parts of this detector. So that's basically what he was saying. So a really heavy one wouldn't be pulled around as much by the magnetic field. So here's heavy, and here's a light molecule. So where they show up here is a function of mass. All right, but what else is it a function of? Before, we said that the radius of curvature is mv over qz. Right? So you look at that and say, well, now we have a problem, because it's not just a function of mass, it's also a function of how fast they're going. And we don't really have any control over that. Right? We blast something to make a bunch of ions, we can accelerate the ions, but they'll all be going different speeds if we give them a certain amount of energy. And also they had a different initial speeds when they started to get accelerated. They don't have the same speed when they come out of here. You can also worry it's a function of charge, but if you think about ions, typically, whatever we do to blast our sample and ionize it, they're all either going to be like +1e, +2e, etc. And you know, if you have a big change, like all the +1e's would be here, all the +2e's would be here. So you can basically rely on the fact that this is a constant. You can assume all your ions are single charge, +1e. And it's a function of the B field, but you set the B field. Right, so you can assume all the ions have the same Q, +1e, and the same B. So we'll say these are the same. But the instrument isn't going to tell you much because really it moves as a function of M and B. Okay? So the mass spec needs a velocity selector. Needs a velocity selector. In addition to this is basically the mass selector. And if they all have the same V, then we can say we're measuring the mass. All right, so now let's look at how you build a velocity selector. Okay? Velocity selector is apply V and E at the same time in some region of space. Okay? So right now we've got our B field everywhere. So we have B sticking out of the board, that's what the dots are. We want to create a uniform E, and of course we know how to do that is with two charged planes, like this. So now we're mixing our B fields and our E fields here. put the positive over here and the negative over here. So think back to the last exam. You should 70% know what kind of electric field that's going to make, because I think that was the average. Right? So the field goes from plus to minus. So here is your E field. That's E. Okay, so we have E this way, and we have B that way. Okay? Now let's think about the little sample down here, your little wet soup that you've made, distilled in acetone, dried onto a flask. And whatever you do to ionize it, you want real specific. There's all the different methods that they use in mass spec. You can blast it with a laser. I think that's the only one. You can blast it with a laser. There are ways to turn the sample into just a bunch of ions flying through vacuum. So let's imagine you're a little positive ion and you've been given some energy and you're moving along with some V. And you're going to have ions of all different V's. So let's think about what would happen to you. When can we pick up our exams? Not now. I don't know. You have to ask Dr. Stinson. He has the exam. Okay, so let's see. So this thing, we want this to fly up and go straight. Right? I, E, and E. And the ion must go straight to get through the pinhole. Right? There's a small hole right here. This is the pinhole. They may not call it that. In optics, we would call it a pinhole. I don't know what they call it in mass spec. The hole. So you can see if one curves its path, it's going to miss. It's going to go into a plate or whatever. So what you got to do is you got to balance FB and FE. Because let's think, as this thing flies through this region, electric force, is it going to feel an electric force? Sure. It's a charged particle in an electric field. It doesn't even have to be moving. Right? This charged particle will feel a force this way, because it's positive and the electric field is that way. Will it feel a magnetic force? Yes, because it's moving. How big of a magnetic force? Depends on how fast it's moving. Right? So the magnetic part is the part that will depend on the velocity. So let's figure out which way is the magnetic force. We want them to balance. So hopefully I've drawn this correctly and it's going to be that way. So here we go. All right, warm it up. V, this way, and I want to cross it with B. All right, I want to curve my fingers towards B. I can try to do that, but I'm going to break my wrist doing that. So I want to, I got to come over here. Yes, B this way and B out of the board. The force is this way. And it's a positive particle, so the force really is that way. So that's good. FE is that way, and FB is that way. So the little thing is going to feel one like that and one like that. Okay? Okay, so let's see. The ion must go straight to get through the pinhole, balance FE and FE to only move straight. Right? See, if they aren't balanced, say FE is stronger, what's it going to do? It's going to go like that. If FB is stronger, it's going to accelerate that way and do that. It will do all these things, but only one where FB equals FE will do that. And only when their velocities equal. And then, once the electric field is gone, to balance, then it will curve. So let's see what would happen if we equate FE and FB. What will that mean? That will mean that QE will equal to QVB. Right, in terms of just the magnitudes. We already got their directions to be opposite, so now we just need the magnitudes to be equal. All right, well, clearly, cancel the Q and solve for V. So only true for V equals E over B. Only these get through. V equals E over B. Well, does that depend on something about the molecule? Or the ion, or the anything? No, right? E over B. We can set B. This whole thing's happening in a big coil. We can make B whatever value we want, and we can set E. We can make E whatever value we want by changing the voltage on those two plates. Right, so that's what's called a velocity selector. As you adjust B and E, you pick exactly what speed of an ion is going to come straight out of this hole. And then because you've now removed function of velocity, because that's now constant, where things land on the strip, on the detector, really do just depend on their mass. And they depend a little bit on their mass and their charge, but you can pretend they all have just one charge. Things with two charges will just show up in a different place. But they'll still be clustered by their mass. Okay, so let's look a little closer at his spectrum here. There it is. He's holding it. The machine prints it out. 20. Oh, like 20 cents.
The results are in.
Oh, zoom in.
You see here we have a massive peak at 3 and
Zoom in
4.
more. Okay, I'll let you see the spectrum. But anyway, you can see it's really sharp peaks.
This now has 10.
You can't see it. But basically, the mass spectrum has it's really high density on X, and it's very sharp peaks because the molecules have very different weights. And this is a very high resolution measurement. Because basically, you can spread it out as much as you want, right? Depending on whatever B you want. You put it in a weak B field, that'll spread them out even more. You can make your detector as big as you want. So you get very high resolution. Ultimately, you're limited by just the magnetic field of the Earth. And that's very, very teeny. You have lots of things you can change. QBB is the force on a particle in a magnetic field. Remember, the force is QB cross B when we were doing the right-hand rule. This is just the magnitude, QBB. FB is QB cross B. Okay, so that's what's really happening in the mass spec. So they did a good job explaining. They just left the velocity selector out. But the velocity selector would be a good thing for a final exam, right? Because it combines two parts of the class. You just have to think about the forces from two parts of the class. Okay. So that's, I think, all we're going to say about the force on a free particle. It goes in a circle. We could talk about aurora borealis and all that, but that's not as relevant to your future as mass spec. Now I want to talk about the force on a wire. Right, here we go. The force on a wire. On a wire. Now for once, I'm just going to write carrying current. But like I said last time, in general, if we say wire during the magnetism part of the class, we're applying it's carrying current. We don't want to constantly have to say a current carrying wire, just a wire. And we're going to put it in an external B field. In an external B. Okay? What I mean by that is that last time we thought about the field that a current makes. Now we're also talking about the field that the current feels. It doesn't feel its own field. We're saying there's some other magnetic field for some reason, and the current is feeling it. Where does the initial velocity of the charge come from in the mass spec? It gets zapped by laser to ionize the material. Blows it into the air. And then they usually have some plates that speed it up. Stuff you don't need to worry about. But they give all the molecules a distribution of velocities, and the selector needs to pick up. But usually it's being vaporized somehow. MALDI-TOF. What does MALDI-TOF stand for? Molecular, blah, blah, laser desorption is probably the LD in MALDI-TOF. Yes, look it up. Tell me I'm wrong. Okay, so currents. Here we go. So here's the wire. Right, like that. There's I. And I'm going to put it in a uniform magnetic field into the board. This. There it is. B in the board. So we just want to think about what force will it feel. And it's pretty straightforward to get it. You say, well, F from a charge is QB cross B. And that's the simple, if we had a free particle moving, QB cross B and it goes in a circle. Or, if you don't like cross products, you can just say it's QB, B, sine, and I wrote alpha for some reason, I don't know why. I think just, variety is the spice of life, sine of alpha. And if you're wondering why I didn't write sine of alpha there, it's because everything was perpendicular here. Right? B was this way, B was that way, so we didn't need to think about the angle. Okay, but we don't have a free charge. We have current in a wire. A free charge goes in a circle, a wire probably doesn't. So one way to look at the difference is to say, well, let's see. If we want to describe this as a current, we know that because it's really charges that are moving with some velocity. I mean, we know that we ought to relate that to the current. Okay, so let's think about the velocity of this thing. It's really then that charge Q, and it goes some length L in some time delta T cross B. That's just another way to think of the velocity, right? Current's flowing along, it goes length L, time delta T, sure, why not? So then you could look at this and say, well, these two together are like a current. How much charge flows through the wire per unit time? That's the current. And L is like the direction it went. So you put the vector on L. Because before, the velocity vector has to be along the length of the wire. Right? So that's what we call L the vector. Just how far does it go per unit time. And you say, well, Q over T, that's the current. So for a wire, you can write I, L, cross B. And that's the force on a wire, the B force on a wire. That's the standard way to write it. Now the key to this is don't think about it too hard. Okay? Because we're not going to have this thing going in a circle. Now you should be saying, well, wait a minute. Wouldn't a free electron go kind of like that and try to go in a circle in the wire? Don't you have little swirling free electrons in the wire rather than just pushing the wire? The answer is yeah, technically. But if you think about our description of how does current move down a wire, we had that thing called the Drude model, which we may not have talked about that much. But it's the idea of the reason you have resistance in a material, even in a metal, is that the electron goes a little bit and it crashes into something and loses all its momentum. And then it goes and crashes and loses all its momentum. And it moves and crashes. So what this thing is doing is it's moving to the side and crashing. And it's accelerating forward and going to the side and crashing. So the force that causes the free particle to go in a circle, here it's kind of causing the free particle to ram into the side of the wire. You can kind of think of it that way. It's not exactly. But if it bothers you that if we use the same equation and we get a totally different result, that the wire feels a force like this, then don't let it bother you. Let's see, I'll probably do that force the wrong way. Let's do the direction now. IL, so L is the direction of the current in the wire, cross B. Oh, I got it right, of course. I'm so intuitive. There we go. There's the direction of the force on the wire. But we could also do it this way. What if we had a B field like this? That. So here's B. And if we had a piece of wire like this, where the current is going through the wire like that, of length L, we could say, what's the force on that one? Okay, well now there's an angle involved, right? So the L vector is like this. And B is like that, so it's just, there's alpha right there. Right? Alpha is between the length of the wire along the direction of the current and B. So there you have an alpha. Here, where was alpha? Alpha is the length of the wire, and then B is into the page. Right, so it's 90 degrees. So that's why we didn't have to write it down. Or well, we didn't write down the cross product. But here, it would be sine of 90 is 1, so it wouldn't show up. But here, you do have the angle. So like I said, this is all inherently three-dimensional. So you got to think about which way everything's going. Here, I really can't put this in the board and give it alpha other than 90 degrees. Even if I drew it like this, the angle between this wire and the direction into the board is still 90. And I had to draw the B field like this to be able to show you alpha. So if you plug numbers in this one, you would just say, you know, I needed to convert this. Sorry. This is ILB. So this is also ILB sine alpha. It's the same conversion. So ILB sine alpha. That's it. That's the force on a wire. It depends on the length. It's force per unit length. And that makes sense. If you had twice as long of a wire in a magnetic field, you'd expect the force to be twice as big. So you can't use the right-hand rule for problems with thetas that are not 90. Yeah, you can. Good question. Can you use it for things that are not 90? Yes, so we can still use the right-hand rule here. Let's say, which way is the force on this wire? All right. L. The vector is L. Well, I don't have the cross product in there. Here we go. L cross B. Fingers along L, right? And curl them towards B. So even though it's not 90 degrees, I can still curl them towards B. Okay, my thumb still tells me that the force in this case is into the board. So this thing feels a force into the board. This felt a force to the right, but maybe you can visualize those as the same thing. They're both perpendicular to B and L. Okay? The only difference is the difference between these two is I have to tilt this in the plane of the board. And it would still feel a force this way. But I can't draw it tilted into the plane of the board. I have to turn it sideways. We're going to do a bunch of little examples as we think about forces. So that's really all it is. QBB, ILB. This is really the same thing. One is for a free charge, one is for a wire. The only kind of confusing part is whether or not it makes something go in a circle. Okay. Force on a wire. So now let's use this new knowledge to calculate the force between two wires. Oh wait, no, I forgot we can do this in the real world.
Oh, sure. We're to go over hopefully some tiredness.
Those are exciting for the video. All right, so this will probably break. This will be fun. Here we go. What we're going to do is look at the force on this wire in a magnetic field. So this is a wire, and this is a horseshoe magnet, or one of these things they were trying to draw in that video that they sort of drew sort of not so well. So a horseshoe magnet has a north pole and a south pole, and normally if you take a bar magnet with a north and a south pole, hands are not strong enough. So normally the field of a bar magnet with north and south, right, it kind of goes out like this, like that. So you have this sort of weird, not very strong field because the north and south poles are very far from each other. It's strong inside the magnet, but we can't get inside the magnet. So that's why you see bar magnets all the time, is they bend it around like this. So then you have north and south here. Right, so then you get strong field doing that. So this is one way, it's sort of the old way, to make a nice, strong, small region of uniform field. So there's a uniform field in there going from north to south. So all we got to do is turn it on and watch it jump. Here we go. Let's see what the wire is going to do. Oh, that pulled it down. So now the other way should make it go up, right? Oh, there it goes. And it's like a toy. This is how I have my fun. I come in here late at night. Just do this. What's the time constant? Okay, so you get the idea. So we're pushing it around. Okay, totally worth it. Now, that is the field. That is the force you would get when you put the wire in an external field. What if you put one wire next to another wire? Ooh, let's calculate that. So two wires next to each other is a very standard calculation, and it lets us think about last lecture and this lecture. So this will be good practice. Force between wires. Here we go. This is good practice keeping up with things here. Oh, let's not do A and B because B is B. Let's do 1 and 2. 1 and 2. Okay. So let's make the currents go the same way. I1, I2. Two wires next to each other with current the same way. What will happen? Separated by, let's call it B. Will they feel a force at all? Will they feel an attractive force? Will they feel a repulsive force? Will they both shift to the right? God knows what's going to happen. And I do as well. So let's think about it one at a time, okay? Wire 1 experiences a field due to wire 2, okay? See, I had due to B, meaning wire B. That would be kind of confusing. Let's do that. Wire 1 experiences a field due to wire 2. Let's calculate it. Okay, so wire 1 experiences a field due to wire 2. So we want the field that wire 2 creates at wire 1. So I'm going to call that B at 1. Okay, so if it's the magnetic field at 1, then we must mean the one due to 2, the field due to 2, because we don't think about a wire making a field on its own. So we got to remember, there's a formula. It's just a question of if you put pi in the bottom of it or not. For a straight wire, you do. So it was mu naught I over 2 pi r. So let's see if we can get all that right. I bet you we can get mu naught right. There you go, mu naught. Which I? Think in your head, 1 or 2. I2. We're thinking of the field at 1 due to 2. So mu naught I2 over 2 pi. And it's usually written 2 pi r, but here, what is r? D. All right, so mu naught I over 2 pi is D. All right, so that's what it feels. And let's get the direction. The direction of the B field that 1 is feeling. Oh, there's hard and easy ways. Let's do it the easy way. We have something straight and something curvy. So just put your thumb along the thing that's straight, I2, and say, oh, the curviness is that it goes around like this. So it's coming out of the board on the left. So out. Out half. All right, so we could even draw it, then this thing is feeling something like this. Okay. Now let's do it. I'll stop. Now we need the force. So now what we've got to do is figure out what force does I1 feel in that field. So what force does I1 feel? And that's ILB. So here we go. Erase this. We've got to get the right I, the right L, and the right B. Let's see. So the force, and again I'll put a 1 because that's the force on 1, is I1. Depends on the current. You know, the force a wire feels in a field depends on the current it's carrying. So this one's I1. L we didn't define, it's just the length of the wires. And then what we call B at 1. So it's just, if I rearrange a little bit, mu naught I2 I1 L over 2 pi d. And that's the force on 1. Now you might say, why are there 2 currents? There shouldn't be 2 currents. Yes, there should. Because that's not the B field. B was mu naught current over a dimension. This is the force. So you have to have I times B. That's why there's 2 currents in there. Let's see. So which way would the force be? More practice. Okay, ILB, IL cross B. There's nothing round here. There's nothing curved, so we're stuck with the cross product definition. F is IL cross B. Oh, I didn't write it. There it is, L cross B. Okay. So L is along the current, and B is out. No, B is out. Oh, it's that way. B. There's the force on 1. Okay. Let's see. And that is the force pre-inflict. I mean, you have to multiply by the. Let's see. Why did we use I2 in the B equation, but I1 in the force equation? Yes, because I2 is creating the field at 1. But when you calculate the force, the wire feels, it's what current does it have. So they're both going to show up. I mean, they have to both feel the problem. So they should. So just think through that later. It makes sense. Now the next question is, what is the force on I2? So if you go way back to 125 prereq, you should be able to tell me instantly what the force on I2 is. It's mu naught I2 I1 L over 2 pi d, because of Newton's second law. Or no, Newton's third law. So this is an action-reaction pair. Now when you're in mechanics, it's hard to find all the action-reaction pairs because there's all these made-up forces like normal forces and friction and whatever. They're not fundamental. Okay? When you have fundamental forces like the electromagnetic force, it's very simple. It's easier to find action-reaction pairs. It's the only 2 forces in the whole problem. Okay? So if this is getting pulled that way, then this one must be getting pulled. You can even get the direction from mechanics. Which way would it have to be to conserve momentum? It's got to be to the left. If you have these 2 things going, and this one starts moving this way, we're going to conserve momentum. This one had better move this way. So they feel the same force moving in opposite directions. And we can run through the handedness real quick. Let's see. The direction of the field in this one would be into the board. Right? Finger along here, curvy, into the board. And then I2 cross would be up. Good. So current in the same direction, they feel an attractive force. So now you can think, if I put them in the opposite direction, do they feel a repulsive force, or repulsive right-hand rules cancel and they feel an attractive force? I'm not going to tell you. I'll let you think about that. Okay, break time. Smoke them if you got it. People used to say that a lot. Okay. Let's keep going because we're going to talk about torque. The first I have a question here. Oh, they said I have a question. I have a question. There's the right-hand rule where you start with your thumb and another where you start with your fingers. When do you use which? So watch the last lecture online for a reminder. There's the cross-product right-hand rule where it's like fingers, curl them, and get the answer with your thumb. And then there's the everything else right-hand rule. Everything else right-hand rule is if one thing is straight and the other is curved, your thumb is the straight thing, your fingers are the curved thing. For the everything else right-hand rule, you don't know which one you're going to start with. It depends on if you know the curved thing or you know the straight thing. So that's why it looks like we're doing different things every time. Are the last equation only true if the wires are equal length? Yeah. If you got into weird geometries where they weren't the same length, the fields would be uniform and etc. That's also an interesting calculation and experiment because that's how they define an amp. It's like if you run the equations, you'll see two wires carrying 1 amp 1 meter apart have a force of 1 Newton or something like that. Basically, actually not 1 Newton, but it's related to the definition of an amp, which is related to the definition of a charge. So it's where the charge definition comes from. Although by now they may have a more advanced definition. But it used to be related to the force between two wires. Okay. So now, at the beginning, we told you the magnetic field is loopy. So now we want to think about the force on a wire loop. So this will be lots of good practice to think about these forces and do the right-hand rule. Force on a wire loop in external B. Right? Force in a wire loop in external B. Let's draw the B like this to the side. Big uniform B field like that. Okay. So here's loop. It's going to be a square loop. Yes, like this. And it's a wire, so I'm going to give it some thickness so it doesn't look like a field line. Like that. Square loop. And the current is going around like this. I know you can't see that well, but there's current going around the loop. And we're going to add up the forces. So let me label them. 1, 2, 3, and 4. So the force on the loop, if we go back to 125, is this the sum of the force on 1 plus the sum of the force on 2 plus the force on 3 plus the force on 4. It's got to add them up. And that'll be the force on the entire object. Okay? So let's add them up. Here we go. The force on wire section 1 is what? Let's see, the current is going that way. B is going that way. ILB, okay? It's a square, a wire loop internal B. Let's say it's a square with sides A. So I didn't quite draw a square, but you get the idea. So it's A. So now we have all the values. And B is just B. So you'd say this is a straight wire, it must be ILB, so it must be IAB. And what direction though? Let's do the right-hand rule. L cross B. So for this wire, L is this way. Okay? And now we got to turn our hand to B. We can't. So if you freak out doing the right-hand rule, you're probably doing it wrong. There's a small chance you're doing it right, and the L and the B are in the same direction. Yes. If L is along B, what's the cross product? 0. Right? We would need to write this one as I, A, B, sine of that alpha. But that's 0. Alpha 0, sine 0, 0. So there's a couple ways to know that the first force here is 0. One is by the angle is 0. One is just memorize current along the magnetic field has 0 force. Or to attempt the cross product and realize, oh, there's no angle, there's no force. How could there be a force? We can't give it an angle. Force has to have an angle. Okay? So this one contributes 0 to the force by multiple ways, however, whichever one tickles your fancy, so to speak. I down. L down cross to B is out. This one feels a force out. Out. And what would the magnitude be? I, L is A, B, and I'll put it down here, out. So run out of room. All right, what about this one? Here the current's going that way. So now L is this way. I'm sorry, L is this way, B is that way. So that would be IAB sine the angle be 180, which is also 0. So if the current is along the field, there's no force. So if the wire's L, the wire's current is along the field, there's no force. If the wire's current is against the field, perfectly, there's no force. Also with the right-hand rule, you wouldn't be able to turn your wrist to the special direction. Let's see. 4 is also IAB, because it's a square, all the L's are A's. And let's just get the direction up. B, it must be in the board. So in hat. All right. So what is the total force on the loop? 0. Right? We have the same magnitude in that we have out. So if you add those as vectors, you get nothing. So a loop in a uniform field feels no force. So current loop in a uniform B feels no force. Main thing to remember. Just like a dipole, electric dipole, a uniform electric field also felt no force. But what did it feel? Torque, yeah. Let's see if we can get a torque out of this. Oh no, let's not get a torque yet. Got excited, sorry. Let's turn it 90 degrees. It meaning the loop, right? So now we got the same field. V, this. And now I'm going to have to draw it with some perspective here. It's going away from you. Look at that. Wow. Did you train at the Sorbonne? Yes, I did. Special physics instructor classes they have there. All right, it's turn. Oh, I didn't turn it enough. Okay, it sucks. Okay, so the current is going this way. Okay, but it's at 90. Oh, this is horrible. Okay. Sorbonne failed me. Maybe that's better. No. Okay, it's at 90 degrees. You get the idea. What is the force going to be? Here we go. So this is the one close to you. 1, 2, 3, 4. Okay. So the force. 1 plus force. 2 plus force. 3 plus force. 4. We'll try to visualize it. Okay. So this one, it's the same loop. It's A, the sides are A. Okay. B is B, etc. So the first one, IAB, but what direction? Or is it 0? Let's see. Up. It's not along the field, is it? None of them are along the field, because it's now turned this way. And so up, I cross a B. This one is still in. This one didn't really change. We just pulled it out. No, we pushed it in this way. So this one is in. Okay. What about F2? This is the one going into the board. It's technically going this way. Okay. I just did a horrible drawing. This way. So it's not going to be 0. It's going to be IAB. It's 90 degrees. All these angles are 90 degrees now. So L cross B is down. Down hat. Okay? So this one the force is in. This one the force is like that. Well, what about F3? I, A, B, because everything's at 90 degrees. You can append the sign of 90 to every one of these. It's the correct way to think about the loop that different parts of the wire still feel force, but they cancel out so that the overall wire doesn't move yet. Short answer is yes. Let's see, number 3. Down. Current down. L down cross B out. Is that what I meant to say? Oh, yeah, well, you would draw it out like this, though. Yeah, I forgot. It's sort of, I'm going to draw them like that, okay? Because it's tilted out into the board, kind of is pushing in, and this is pulling out. That's how I'd rather draw them. But you get the idea. In, out. And then what about this one, IAB? F4. 4 is coming out of the board. Out of the board, cross this way, up. In, down, out, up. the loop is like this. In, down, out, up. We're compressing the wire. So now if we turn it back and look at it. Compressed. Force is still 0. Right? There's no force on that wire. There's no net force. The net force is 0. Add them up. Okay? So note that we turn it both ways, we still get no force. Cool. Exciting. Okay. But it does feel a torque. That's the idea. But the force applied, forces are applied to different parts. So there may be a torque. The way torque showed up in 125 was that we said everything isn't a point object. Things aren't point particles, they actually have a size and an extent. And you can think about their orientation. You can apply forces to different parts of it. So that's totally true for a loop. We're applying forces to different parts of this movement. Okay? So let's think then, what is the torque? Or does it feel a torque? Maybe it will have a torque. All right, so we're going to go back to the first one. Here we go. Add squares here. Like that. And I've still got the current just to be consistent, going around like that. And we had the force. There was no force at the top. There was no force at the bottom. Here, that was F4. And here was F2, using the same notation here. So you can kind of look at it and tell there's a torque. If it's a free particle, it's going to rotate around something going through its center of mass. It's a free object. So clearly we're rotating around that axis. The axis perpendicular to the forces and through the center of mass. It's basically how it'll rotate. So if you want to, so this is rotation. If you want to calculate the torque, you can remember back to 125 if you remember the vector form, or if you remember the give you the angle form. But basically torque is R cross F, if you want to be fancy about it, or it's just RF sine theta if you just want to calculate the magnitude. And you got to get the direction from the right hand rule. Although we didn't even do the direction last time, but okay, in 125. Okay, so let's think. What is R cross F? We're going to define those vectors first. What is R? So if you're doing a torque, what is the torque vector, or what is the R in the torque vector definition? It's from the axis of rotation to where the force is applied. I hilariously got that backwards one year, and I insisted that I should. That might have been last semester. So this vector is A over 2. Right? The vector all the way from one side to the other is A, because that's the length of the square. So this one's A over 2. It's a square of sides A. So the vector is just A over 2 from left to right. The force vector is just the force vector. IAB pointing in. So if we want to get that, then it's just the product of those. The product of the magnitudes, 1/2 A times IAB. And the direction is from the right-hand rule. Right? So we say A over 2, good, crossed with the force, R cross F, down. It's saying that gives you a torque vector down. Right? Torque is like a tau of the vector. Torque vector down. There is a non-cross product, easy right-hand rule way to get it. If you look at this physically, you can tell which way it's going to want to turn, right? You kind of tell. It's sitting here, this side's getting pushed that way, this side's getting pulled that way. It's sort of going to spin like this. So make your fingers move how it's going to spin. And your thumb is a long towel. It always works. Can't go wrong. Anyway, if we do R cross F, we get down. If you want to do it this way, you would just say R, 1/2 A times F, IAB, times the sine of 90 degrees. What's the sine of 90 degrees? 1. So you'd say it's 1/2 A IAB, and you'd be on your own to get the direction that it's down. Okay. But that's just, this is due to F4. Okay, so let's add in F2. What's the torque due to F2? It's either going to cancel or it's going to add. Right? One or the other. Let's see. R is also 1/2 A. There's R in this case. F is in IAB. And they're perpendicular, so we're just going to get the direction from the right-hand rule. A, or 1/2 A cross F is down. Oh, thank God, they're both down. And this is F4. This is F2. Their contributions to the torque. So the half just goes away. It's IA squared B. IA squared B is the torque. And it's down. So from like this, we could set it up backwards. We could say this loop is in the uniform magnetic field to the right, and it's spinning this way. Which way is the current? So you could work your way backwards to say, oh, it must be this way, that way. So you could go backwards. But what's interesting is that the torque here is the current going through the loop times A squared times B. Well, what is A squared? It's the area, isn't it? Is that a coincidence? No, there are no coincidences. Are there degrees of coincidence? I don't know. Let's see. Here we go. So here's the mind blower. Are you ready? I actually got too cool though. Like, it turns out, let's just say this, any shape loop says this: the torque is IA B. So it doesn't matter if it's a circle or a square. You just got to think about the current in the loop and the area of the loop for any shape. Doesn't matter what the shape is. But now the tricky part is we got to make one of those a vector. Somebody has to be a vector around here. Let's see. Is it a correct way to think about the loop in different parts? Oh, yes. I thought the torque was just how the object rotates, which has nothing to do with the down vector, right? No, so torque is a vector. We didn't talk about it last time. In 125, 126, we didn't do enough rotational stuff to have to treat it as a vector. But torque is a vector perpendicular to the plane of rotation. So everything you understood about torque is correct. It's the force around a curve that makes something turn, etc., etc. But when you get more advanced and have to treat it as a vector, if something is spinning, which way is it spinning? You can't put a vector on which way it's spinning in the plane because it's constantly, everything's changing direction. So the direction of something spinning is perpendicular to the plane that it's spinning. So that why that torque vector down means the thing is spinning like this. So that's an important concept to get in there. And then, new question is the rotation axis always perpendicular to the magnetic field? Oh, where did my head hurt? Oh, I think so. I'd have to do a bunch of examples to be totally. The rotation axis, no. Yeah, I don't know. We'll do enough examples and decide. Okay, so we need to make something. Something has to be a vector here, right? If this torque is a vector, IAB, clearly B is a vector. So is I a vector or is A a vector? Actually, A is a vector in this case. Does the torque tell you if it spins left or right? Yes, by the right-hand rule. You just asked, is the torque something straight, a vector straight, tell you something spins, something curvy? Right-hand rule. Right? So if all I told you was the torque on this is down, you put your thumb down and say, oh, it turns that way. This goes into the board, this comes out of the board. So yes, the torque vector does tell you something spins. That's the point of the torque vector. Y down for torque when the loop moves clockwise, and it's spin up or the opposite direction. Depends on what side you're looking at it from. If it's clockwise, if you look at a clock from the back, is it still going clockwise? Not sure. So think about that. Stick with the right-hand rule. Okay, we got to move on. Here we go. So where are we going to get a vector? It's A. We define A as a vector. Oh my God, why would we do that? So it's like this. So say you have a magnetic field, right? And B is like that. Let's just say here is a little. Here's a little current loop here. It's round. And it doesn't matter, we don't have to calculate the area, we just know it has an area. A. So A is a vector perpendicular to the plane. Okay, so every little loop that you have has its own little vector moving around with it. Okay, and the magnitude clearly is just the area of the loop. What about the direction? All right, I could have drawn it this way, couldn't I? I could draw it this way or I could draw it this way. Why did I draw it that way? The direction from the current. And the right-hand rule. All right, so I must have had the current going this way. Did you see my on-the-fly right-hand rule? That was behind the notes. I'm doing the right-hand rule when I'm doing that. All right, so the current was like this from front to back. So that's how I knew that A points out that way. Okay? Okay, then the final thing to tell you, just to make it a little worse, is IA is so fundamental, it gets its own name. Call it the magnetic moment. That sounds kind of, romantic. Let's have a magnetic moment. And that's what we talked at the very beginning. Remember what I told you a little bit about magnetization has no charges, it only has dipole moments. Just like you have the dipole moment of a charge is a plus and a minus, magnetism is all based on that same idea, kind of like a plus and a minus, or a north and a south. You can never separate the north and the south. All you have is the moment. Okay, so it's called mu. So here, if I had the same loop, and it's sticking out on this side, it's going in there, and the current is going this way, I would say that vector, I'm going to call it mu. Okay, and mu equals IA. So just, I've run out of room. Mu equals current times the area vector. So every problem you do, you could say, I don't want to deal with mu. I'll just multiply I times A every time. It's the exact same thing. What we're trying to show here is that the fundamental thing that's important in magnetism is the current and the area. It doesn't really matter the shape or the geometry or anything like that. I didn't really prove it. In other classes, if we had more time, I would go through and do like 3 different shapes. And we keep getting the same answer. You can do a circle, pretty easy. I can do a triangle. Give me a couple hours, I can do a hexagon. But no matter what you do, you get the torque is IAB. That's how we know that IA is a very fundamental thing. Okay? So the magnetic moment is kind of like the charge in magnetism. It's the fundamental thing that tells us how things move. Right. So all we got to do now is think a little bit more then about sort of how is that going to move. Now we're going to think just in terms of moments. Remember, moments are just current loops. So let's draw a couple more diagrams. Practice a few more things here. This is all from the beginning. This is force. Think about force. So now, let's think about the energy of a moment. If you're cool, you don't have to say magnetic. You just call it a moment. Of a moment in a uniform beam. There you go. Energy of a moment in a uniform beam. So let's draw a uniform beam. Here, it just means a magnetic field to the right. It's got some solenoid or something. And let's start with our moment like this. There it is, pointing up. There's our magnetic moment. If you want to think a little bit about what that means, it means it's got an area pointing up. That must mean that the current is going this way. This is the front. I'm going to specify the front. I usually put the front lower because I'm always above everyone. Okay, so it's going like that. So the current must be going like this. Current going front to back like that. I going like that. A must be up. Mu must be up. All right. So what are we doing here? I don't know. So let's say what torque would this be? So we're going to call this 1. So 1. What torque? All right. Torque was IA cross B. Torque must be mu cross B. It's the shortest way to write it. Torque is mu cross B. Or if you want, mu times b times the sine of the angle between them. Okay? So here, the sine of the angle between them is 90. Mu b sine of 90. All right, sine of 90 is 1. So it's equal to mu b. I'm not going to write it as IA. I could, but we're trying to think in terms of the moment. So we just tell you it's a little atom at a certain moment. Okay, so torque is mu b, but which way is the torque? Lots of ways to think about which way. Well, one way would just be to say mu cross b. Which way is mu cross b? B is here. Get your hand out. Wipe it off. Get it ready. Mu cross b. The torque must be into the board. So there's your torque vector. Torque is in, out. Torque into the board. Which way is it going to rotate if the torque is into the board? Now we got our low-calorie right-hand rule, our non-mathematical one, and say, well, which way is it going to rotate? Well, I put my thumb along the torque. Oh, this is going to go down, and this is going to go up. So in this board, it's going to rotate clockwise. It's going to rotate like that. So it's going to end up like rotate to a position that looks like this. Okay. So let's say it's going to be mu, b, it's going to, 1 will rotate toward, which way, if that goes clockwise, it's going to be like this. Like that. And it rotated clockwise. And when it gets to there, use this way, right? And mu is along b. We're going to call this position 2. 1 will rotate toward 2. What is the torque now? 0. Okay? Because torque is mu cross b. If I try to do my hand along mu, I can't do a cross product. If I do the magnitude, I say mu times b times the sine of the angle between them. It's along it's 0. Sine of 0 is 0. So just like when the current was along a magnetic field line, you got no force. When the moment is along a magnetic field line, you get no torque. We went back to our discussion of the square loop. This is the case where it was just being compressed. We didn't calculate it, but we would have also gotten no torque in that case. So here the loop is just being compressed or expanded. I'm not sure. I have to do some math to figure that out. Okay? So what we're seeing here is the torque on a dipole. I'm sorry. A magnetic moment, or just a moment, tends to align with a uniform beam. And a non-uniform beam, but that's something else. With a uniform beam. If it was not aligned, you had a torque going that way. You go through the exact same arguments, and if you had it turned down and it wasn't aligned, the torque would pull it this way. If you had it all the way turned the opposite direction, there would be no torque, but as soon as you deviated a little bit, it would get pulled all the way around. Okay? This is exactly what a compass is doing. All right? So for a compass, this is your little bar magnet. And a bar magnet has a magnetic moment. So if you think of a bar magnet, you just think of a little mu vector sticking out of the North Pole. Okay? And it wants to line up. So we can finish by calculating the energy. Now I'm just going to tell you the energy. What's missing here? Oh, here it is, yeah. So hopefully I didn't quite go through as many examples in a minute, but hopefully you get the idea then that, say it's here. If you just let it go, say it's up here. If you just let it go, what's it going to do? It's going to rotate and pick up kinetic energy. So therefore, this has a higher energy than that, right? So this must be the lowest energy. Because if I wanted to turn it, I'd have to push, I'd do external work to get it back over here. So to do external work gives it potential energy. So when it's aligned against the magnetic field, that's high potential energy. And when it's turned all the way there, that's low potential energy. So the U, the potential energy, is minus mu dot B if you're in the vectors, or minus mu the cosine the angle between them. That's just like the potential energy of a dipole in an electric field. It's the same idea. Here, if it's aligned, theta is 0, cosine is 1, you get a big negative potential energy. If you turn it all the way, counter-align it, theta is 180, cosine of 180 is negative 1, negatives cancel, and it's a huge energy. So that's why they go back and forth. Now, if you let this go all the way, it has kinetic energy. It'll actually oscillate. And that's why, like, a fancy, what's it called? Compass like this doesn't stop. It keeps going back and forth. That's why compasses have water in them, is it damps the oscillations. They get there, and then they don't keep going, because they're damped. Okay, that should be enough to do the homework on forces and torques and fields. We'll do Faraday next week.
So for this one, you put your and you point down. And then why does this one go out instead of in? Yeah, because this is the current point. So this is the point. I mean, that, okay. This is that way. This is this way. So in this case, here you go. What do you want to do? You're right.
Don't erase this off the book. You got it here?
Yeah. The F2, for example, the Atari display episode isn't worth it.
So,
Oh, did I connect the switch and out?
yeah, that's
Oh, okay, I got confused back.
we could do a workshop. Yeah, this is a little.
did those exams, and then I'm gonna see if I can't send out.
Okay.